Hello everyone and welcome to the second episode of memflow Applied, a series where we will be making a practical project that is a pattern scanner. Well, in this episode we still won't be going into detail about pattern scanning, memory scanning, pointer scanning, and anything like that. I'd like to take this episode as an opportunity to talk about performance in memflow and how to squeeze everything out of it in the best possible way. So in this episode we will talk about caching, overheads, batching, and we will talk about other ways to improve performance and make your programs really fast. This will give you a clear understanding on how to achieve good performance with simplicity. So without anything further to do, let's get started with the video. When talking about performance, the first thing to do is to quantify it. So we will go back to our program, and this is our program which we wrote in the last episode. And what we want to do is test out how fast it runs in a repeatable fashion. So what we just want to do is actually just test out how long reading all of the memory takes. We want to rerun the program multiple times, so we just remove the final step of overwriting the flag, and we remove our break call so that it reads through the whole module. And once we have that, we just cargo run release. It builds it, it runs, it asks for password, so it finds a match, everything works as fine. And what we just do is time it. Time the execution time. Time the execution, and you can see it's about 2.7 seconds. It's like 2.8, 2.7, sometimes it's 2.6, but it's roughly about 2.7. We can do much better. And to do that, I'll first talk about overflowing that like button. Seriously, guys, my goal is to get to negative 2.1 billion likes, and that first involves going over 2.147 billion likes. So please help me get there. Your like helps me tremendously. Thank you very much. And the theory side of things, the bottlenecks and everything regarding that. We need to talk about what kind of overheads there are when performing memory operations. So when you perform your operations, you have your app, which does memory reads to the connector. The thing is lagging due to recording, but with the connector, and it goes here, but it doesn't go directly. What happens in between them is a process called virtual address translation, and that is right here, this box, and it's a VTOP. And this VTOP, what it does, it actually, for a single read, it performs four physical reads. So what we have here is a virtual read. Right here we have the translated physical, and right here we also have 4 physical reads to determine the physical address for this single virtual address. As you can imagine, it's rather a lot of work. And mind you, if we read a single page byte by byte, what you have then is a box which is repeated 4096 times. So to read 4 kilobytes, you need to actually read, well, 5 times that because of this. And there are a few overheads. First of all, it's this virtual translation, which is overheading, and then the connector itself, it has some overhead into performing one single operation, and another overhead being its bandwidth. But most of the times you won't actually reach the bandwidth limit because of the single call overhead that you will be reaching. How do we solve this? Well, we can solve this by something called batching. So we have our app once again, and we have our connector once again, and we have VTOP once again, and it links like this, links like this, links like this. What we have now here, let's go from the start. We don't submit one read operation. Instead, we submit 4,000 of them. So right here, we have virtual reads. It's a batch. Once you have that batch, what happens is we go to the VTOP step. And VTOP, surprisingly, since it's all in the single page, it can translate all those 4,000 elements in the same number of calls, in the same number of reads. That is 4 reads, 4 physical reads. And this is not batched in any way. And once we perform that translation, by cutting down a lot on the virtual translation, what we can do here is actually submit 4,096 physical addresses, and it's a batch. What we have here in total, 1x. We do this whole thing once. What happens is, first of all, we cut down on virtual translation reads by 4,000 times. And we submit only one call to the connector, and which means we lower the overhead from a call to the connector, and thus we get a much higher performance. Well, now let's actually test this out in practice, shall we? So, just to test again, we take 2.7 seconds to read through the whole module. Let's first go ahead and do batching using the so-called batcher feature of memflow. So what we have to do is first define enough buffers for the batch size we need. So we will be using a little bit more memory in our program. And what we do is buffers, and it's a vector of vectors that are that are like all zeroed target string length. And the length of this is the batch size, which let's just say is 16. What we have to do now is go right here and step through the program by the batch size. And we will comment this whole thing out. We will compare it later on. And what we have to do is create a batcher instance. And that is process virtmem, and it's a virt batcher. And once we have that, what we do is go through every single one of those buffers and queue a read to that. And that would be for buff in buff.hrmut. And we need to get the offset within the which batch number it is, so we know which address to read. So we enumerate everything, and we get a for loop from 0 to 15, including 15, with which we will use for batcher read raw into, and we read into base plus I plus O, and it will be the buffer. You see, this is a bit different from here, because this by itself is a reference, mutable reference, because we iterate the references, so we don't need to mutably borrow it again. And once that's done, we just need to check through all of these reads whether or not we find a match, because if we just read and don't find a match, well, what's the point? So to do that, we need to first dispose of the batcher, and that will be, you can dispose of the batcher or create a scope, which dispose of the batcher. When it gets disposed, it performs all these operations for you. And once that's done, what we just do is we go back through the buffers and enumerate them all once again. And what we just do is, once again, we compare if the buffer is equal, and we convert this as slice. Once that's found, we just print out match found and base plus I plus O. Once that's done, we time it, and you can see that our runtime dropped significantly. It dropped all the way down to 0.5 seconds, from over 2 seconds to less than 1. 4x speed up, 4x speed up, but we can do better. And we can do better by actually controlling the batches ourselves. Batcher is really nice, but currently it performs quite a few memory allocations. So if you were to control the batches yourself, you could avoid them. And if you can avoid them, you have more precise control and better performance. Let me show you real quick how to do that. And that will be, what we need to do is build batches ourselves, and that involves importing virtual read data object. Once you have virtual read data, we will comment this thing out. We add another vector, read equals, and it will be a vec. This time around, what we will do is use a little bit of iterator magic, and what we'll do is buffs itermut.map. So we go through each buffer and map it into a virtual read data object 0.into. We currently set the address to 0 because we will be looping through them again later on, and it will be the buffer is B. We map them through into this virtual read data object, which borrows all these buffers, and we won't be able to interact with buffers again until we dispose of reads, and we just collect it into vector. And once we have that, what we do is right here, we go to for O and RD in reads dot mutable iterator and enumerate once again. What we do here is now set the address, which is the first element of the tuple struct, rd.0 equals base plus I plus O. And once that's done, once we loop through all of them, what we can do is do process virtual memory virt read raw list. We read the whole list of data, and that will be reads dot as mutable slice, and we take a partial result, and once that's done, we did the reads. And once the reads are done, we do the final step, which is we unpack the actual read data, and that will be address buff in reads.iter. We iterate through all of them, and what we do is just check target string equals buffer as slice. We don't do as slice because this is already a slice, and we print out address directly because virtual read data includes the address. And we run it again. A slight bump in performance. It goes 0.49, 0.50. Let's see how, if we were to increase the batch size to 128, we have performance in the lines of 0.36, 0.36 with using the automatic batcher. And if we were to use the manual batching, it's supposed to go down a little bit. 0.34, 0.35. So we don't gain much performance out of using batcher, and depending on batch sizes, as you can see at 128, we get a little bit of performance ahead. And if we were to increase this to the whole page, 4096, we get the very sweet spot at 0.35. But you can see they're not very different, but if you want to squeeze out the most, you will probably want to use manual batch handling, which we will also be doing inside as we code the pointer scanner. We've gained quite a lot of performance. In fact, it's like 10x speed up from 2.7 seconds to 0.35. That's more like 8. But there's one last trick we've got up our sleeves. You see, we did optimize the call overhead, but we can do even further, because if you notice our reads, they're done byte by byte, byte by byte, with the length of, I think it's 18 or something. So we have 18 bytes here. We then shift and read 18 bytes again. Shift, read 18 bytes again. Shift, read 18 bytes again. As you can see, every time we have like 17 bytes overlapping. And the same byte gets read 18 times. So we can actually very much cut down on that. And how do we do it? Well, what if we just issued one single read call for the whole page and then go through that page and just get our performance back again? So what we do is we totally comment this part out. We're not going to use it. What we are going to do is create a buffer, which is of length 4096 plus target string.length -1. Why do we do this? Well, if we were to read page by page, we need to also count if the string crossed the boundary between two pages. So we overread it a little bit every time. So there is a little bit overreading and a little bit of overlap, but very tiny bit, very sparsed out. So we read like 4 kilobytes plus 17 bytes. And what we then do is step by 4 kilobytes and do simply process virtual memory, virt read raw into, and that will be just base plus I, and it will be buff as mutable slice. Take a partial result, and yeah, we have that. And what we're just gonna do afterwards is do some Rust iterator magic, and that is for, the offset. We take the offset and the buffer in buff times windows of size target string.len. What Windows does, it takes a slice and cuts it into small sub-slices, which go through the whole slice, byte by byte, essentially, and allows us to check individual sub-slice very efficiently. And we just enumerate it all. Once that's done, we just perform our checks. We perform our checks, and it will be the same as using the batcher. We don't do a slice because it's already a slice. And as you can see, we get an insane amount of performance. We go down to 0.08, and it's like absolutely insane. All of this 0.08 is mostly initialization time. It's not even, the reads. They're so fast, so efficient, that we're taking literally no time whatsoever. And it's incredible. So yeah, these were the ways to optimize your code for high performance. There's one last thing I should mention, and that is caching. Caching is a feature of memflow that basically speeds up quite a few things in order to make performance fast for free. And how do we do it? Is from the last video, here we go, build default caches. And that's pretty much it, to be honest. So yeah, let's see what happens if we don't build any caches. We jump, for this particular thing, we don't have much decrease in performance. But what if we go back a bit and do manual batching? What we have here, we go down to 0.2, which is interesting because there is a little bit of overhead in virtual translation cache, which we basically avoid by doing all the translations in batched fashion. And we can just do that by build page cache. So we take memory and architecture, and we just do arch. As you can see, we go down quite a bit by just using the page cache, but VAT cache slows down a little bit when you perform batched reads. So with page cache, you gain some essentially free performance using page cache. And if we turn it off, we go down to 0.20. Just enabling page cache, we go down to 2.5 seconds, which is funny, which is very funny, because that's still faster than, than using VAT cache. It's so funny that using VAT cache makes things go slower. That's something to note. And on that note, that's something to change in memflow by default currently. So VAT cache is makes things a little bit slower on Kimu because it's mainly meant for really fast connectors like KVM that don't benefit from page caching, but might benefit from cutting down a little bit on the virtual address translations. So that's where the VAT cache comes in. But currently, it's not very useful in most scenarios. In most scenarios, it may not be super useful. And we may need to disable that. But yeah, on that note, this was it. This was an episode on making performance go vroom. So yeah, thank you very much for watching. In the next video, we will actually go into making the pointer scanner. It will be very fun. So yeah, thank you for watching. Don't forget to like, subscribe, hit that bell for more videos like this. Share it with your friends who might be interested in DMA. And yeah, thank you for watching once again. My name was Heap. Yours was Undefined. Bye-bye. It's a bit shameful that our default caches are not really best settings, but yeah. Anyways.